Hello everyone, my name is Alex Zades, and I've been working with Dr. Howland this summer on designing a star coupler to perform an optical Fourier transform. I'm super excited to show you what I've done, and I hope you enjoy this presentation. So before I start, I want to go over the objective of this project, which is to replicate a free space optical Fourier transform on a chip, which isn't as trivial as it sounds, if it even sounds trivial, but we kind of did it, so I want to show the results. I think they're really interesting, so we'll get into that in a moment, but I also want to touch on some of the topics I'll cover in the presentation. So I'm going to go over the background, what's a Fourier transform, what's integrated photonics, what is the star coupler, and then I'm going to go into, what I explored in the research, uh, radius versus transmission and fidelity, and are tapers good or not. All this stuff we'll get into, and you'll probably know what it all means by the end of this. And of course, some future work like diffraction gratings and inverse design are very interesting pathways that this research could go moving forward. So let's get started. So first I want to talk about the applications of the project because I feel like it's valuable to know why we're doing something before, you get into all the nitty-gritty. So almost all applications of Fourier transforms in general lie in the realm of signal processing. And some of the just specifics are spectral analysis, pitch correction for all your favorite artists singing. That auto tune really has to come with that Fourier transform. Um, Radar systems, image reconstruction. The main reason we're doing it is for momentum correlation. And I'll explain a little about why we're doing it and how in a couple slides. But it's just important to know that's the reason. So let's go into the Fourier transform basics. You may not need to hear this, it's used in a lot of scientific fields, but I thought I'd go over it anyway since it's an undergraduate conference and, I didn't know what it was a year ago. So Fourier transforms are a way to convert a signal from the time domain to the frequency domain. And this is done because a signal of any type in the time domain can theoretically be reconstructed out of a combination of sines and cosines at different amplitudes and phase offsets. So if you add enough of these sines and cosines together, you get the same signal that you came in with. And that's kind of what this visual represents. You can see that these signals are being made up of a bunch of smaller, different frequency, different amplitude signals. So what's an optical Fourier transform? Well, an optical Fourier transform is essentially the same, except you're decomposing an image into a superposition of plane waves. And those waves are traveling in different directions, and they have different amplitudes and phases. And it's basically the exact same concept as just a regular mathematical Fourier transform. It's just with a two-dimensional wave rather than a, a frequency making up like a sound or something. Now I'm going to briefly go back to the momentum correlations. We are using the momentum correlations to check anti-correlations for QDITs. And it's a very complicated process. Even I don't fully understand at this point. The math's a little over my head. I haven't taken the requisite classes to completely understand it. But the star coupler allows us to check if we have path correlations and momentum anti-correlations. And we therefore can use the star coupler to check if we have entanglement. That's the very cursory explanation of what is happening and why we need this device. And it's not necessary per se. You can do this in free space optics. We'll talk about that a little more later. But it's much more efficient to do it on the same photonic chip as the QDIT. So now I'm going to talk about what integrated photonics is, because that's kind of the whole realm that this project takes place in. Integrated photonics is a field of building nanoscale devices that manipulate light, kind of like we build microchips that manipulate electricity. So this allows us to take these massive bulk optic setups like lenses and lasers and all this other stuff and put it onto a tiny chip. And doing that allows us to more directly manipulate the light because our structures are on the same wavelength scale as the light itself. So it allows us to do much more interesting things with light. That's just a basic overview of what's going on. You don't really need to know more than that for this presentation, but it's a very interesting field. You should definitely look into it. All right, for the big money, what is the star coupler? Well, long story short, it's a device that performs the same thing as what's happening in this image on the left, where you have an input image that goes into a lens and then is projected into the Fourier plane. And so basically the lens takes the Fourier transform of the image. And that's exactly what we're doing with the star coupler. The fact that these waveguides, which are the rectangles on the right and left, go into this free space region, which is what the centerpiece is called, at confocal angles to each other, actually creates the exact same setup as what's pictured on the left. And it's performing a discrete Fourier transform, which is essentially just a Fourier transform, but with finite numbers of inputs and outputs. It's important to note that we have about 2 degrees of freedom. And I say 2 because there's actually 3, but there's only 2 that really matter. The R, which is the radius of the device, and N, which is the number of input and output waveguides. For this to work, there has to be the same number. One of the requirements of this device is that it's performing a unitary operation, which means it has to be lossless and work backwards and forwards to replicate exactly what's happening in free space optics. One quick note is that the 3rd degree of freedom comes from how large the angle of the free space region is. If it's too small and it goes up against the waveguides, that's that top edge, then you get reflections, which clutters up your output signal and makes the fidelity worse. So what are the actual challenges and design considerations with making this? Well, the information for making it was somewhat limited. There was about 1 paper that had a good explanation of how to do it, which is cited in the slide above. But we can make it small, where the free space region is small and the waveguides are closer, or we can make it large, where the angle between the waveguides is lower, but the free space region is absolutely massive. Or we can make it with tapers, where the waveguides get bigger as they approach the center free space region. There's also considerations like grading structures, which I'll talk about a little later. And in doing this, there have been several problems with simulating it, mostly because Lumerical's 2.5D simulations are very quirky and don't like to work. So the transmission data is not exactly perfect, but it should illustrate the point. All right, let's talk about the size and the transmission. So making the device bigger decreases the transmission. And this is mainly because when you make the device bigger, less light actually goes into those waveguides. It spreads out more in that free space region as it propagates through, and it hits walls and it scatters and it diffracts and it reflects. So you're losing a lot and not as much as going into the waveguides at larger sizes. And we'll talk about why making it large is not necessarily a bad thing in a moment, but the main takeaway is you make the device bigger and the transmission gets worse. So let's talk about how size affects fidelity. So as you make the device bigger, then the fidelity increases. So if you can see that in this animated graph here, as the device gets bigger, the actual signal starts to match the projected one. So the projected signal for a single input in a fast Fourier transform is just a straight line across all the outputs. And this is all normalized. That's why it's at 1 instead of whatever it would in reality be at. But this device does start to do that very well as it gets very large, at about 300 microns. The problem is, as you can tell from the last graph, the transmission at 300 microns is relatively poor. And this presents the problem with making this device. The bigger you make it, the more lossy it gets, and it can't be lossy, and it still has to be accurate. Now, I'll talk about some ways to remedy the problem of loss in a moment, but I think it's important to recognize that the device does do a Fourier transform, just not very well. And this graph on the left shows the actual light in the device and where it tends to be most often. So the highlights are where it is most of the time. That's where the intensity is greatest. While the dark parts are where the light tends to never be. And then on the right, we actually have the input and output of the signal that was put into the device. And as you can see, it is relatively close and matches the features of the ideal input signal, just with that envelope that we kind of saw from the graphs before, where at farther away from the center, it starts to decay more. Here's another visual of how the device is actually performing. I think this one's very interesting because it's a double slit, and you can see that interference pattern in the output waveguides, which is really cool. So again, the device is properly doing a Fourier transform, it's just not lossless. So let's talk about a couple ways that we could potentially make it lossless. Let's talk about tapers, since they're a potential way to mitigate this loss problem. If you can absorb more of the light once it hits the edge of the free space region, instead of just hitting a wall, it'll just go into the waveguide. And on paper it sounds good, but in practice it's not amazing. So I've run a couple simulations. Below are the results. There's a double slit one, and there's just a normal, only in the center waveguide one. And the results of these show that the fidelity is worse than in the double slit one for the more complex signal, but for the simple signal, it's definitely higher than the original one, which means more of the light is going in. The transmission is higher for this device. There are many ways I can do the tapers. You can also taper to a smaller width, which blows out the mode. That's just a special property of, these on-chip photonics. But that also doesn't seem to fix this problem, since no matter how big you make the tapers, even if they encompass the entire edge of the device, then it's still not lossless. So I'm going to go into a couple future ways to potentially make this device lossless. So the most promising method is diffraction gratings. So a diffraction grating is essentially a wall with a lot of slits in it. And when light passes through this, a plane wave passes through this wall of slits, then you get interference after it, where the light interferes with itself, and you get constructive interference and destructive interference. And as you can see in this diagram, there's constructive interference that produces peaks along this output plane. So the potential idea is to use these diffraction gratings after the input waveguides to focus the light towards certain points. And hopefully those points are the output waveguides. So designing a diffraction grating that does that would still preserve the interference that happens in the free space region, but also prevent us from having to make massive tapers or make the device very tiny to just keep the transmission to anything reasonable. But I still have to explore the grating shapes and the placement. Is it going to just be one in the center? Is it going to be right after the waveguides? There's a lot to do here, and I hope to explore it more. Another potential method is using inverse design to design tapers that are not linear. So inverse design is a computational technique that allows you to use the computer to just design a device, essentially. So you tell it a target for whatever parameter you want to optimize, whether it be maximizing the transmission and fidelity or minimizing some other parameter. And then the computer will try different permutations of the device within, a specified range, and eventually find the best solution. It's very computationally intensive, but it allows you to get solutions that, no human could ever think of. So that's another potential way to actually improve the way this device performs. But first, I think the diffraction gratings are a better path to explore. And then this can be a second thing. And maybe both in combination would improve the way this device performs. So in conclusion, I've explored many different ways to design the star coupler, from increasing the radius to changing the number of waveguides, all sorts of things I've looked at, and I've qualitatively evaluated that increasing the transmission results in a decrease in fidelity, and finding a good balance between them is very difficult. So potentially using solutions like diffraction gratings and inverse design may be a great way to continue this project and move it forward to the eventual goal of having a lossless star coupler. It will never be perfectly lossless, but it can get very close, and I'm confident that these future techniques will definitely improve the performance. I just want to thank Dr. Hallen, my advisor. He has helped me so much through this project. I could not have done it without him. There's so much I do not understand, and it's been a very enlightening research experience. I also want to thank Dr. Preble. He's extremely smart and knows so much about integrated photonics. He taught photonic integrated circuits class this semester, which was super enlightening and has allowed me to do this work. And I want to thank Delaney Elliott, John King, and Matthew Merrick for helping me with this project. They've given a lot of suggestions and feedback and helped me get to the point where I am today. So thank you for listening, and I hope you have a nice afternoon.